So in the previous class, we discussed about the transformation operation in each round, right? And we covered the first and second operation, the first and second transformation operation, which were subbytes and shift rows. Okay, in subbytes, we were doing the intra-byte transformation, right? And the shift row operation, we can say that that is a byte exchange transformation, right? So we also need an interbyte transformation that could change the bits inside a byte, because in the previous two operations we have not operated on bit level, we were operating on byte level. So we need an interbyte transformation which could operate on bit level, which could make changes in the bits inside a byte. So that change must be on the bits inside the neighboring byte. So in that change which we will be applying to the bits inside the byte, in that change the neighboring bytes must also be involved. Okay, so for this kind of interbyte transformation, we use mixing operation, which is the third transformation operation in each round, right? So we need to mix bytes to provide diffusion at bit level. So this mixing transformation, it changes the contents of each byte by taking 4 bytes at a time and combining them to recreate 4 new bytes. So it will again, it will be considering 4 bytes at a time. So we'll be considering a column matrix of 4 bytes out of the state, and we will be dealing with that matrix. Okay, we'll be changing the values in the bits of the bytes which are there in those 4 bytes. So to guarantee that each new byte is different, we what we do, this combination process, it first multiplies each byte with a different constant and then mixes them. Okay, and for this multiplication process, we use this constant matrix. So this is just an example. I'll show you the constant matrix. So we will be multiplying the column matrix with which we are dealing at a time to the constant matrix, and the result will give you the new matrix, okay, which will work on the bit level, right? So this is how this mixing is done. So how we do this, we can use this is one of the example of constant matrix which we could use for this mixing operation. And the operation which we perform while performing this mixing, we call those operations as mix columns and inverse mix columns. So mix columns for the encryption side operation and inverse mix column at the decrypting side operation. And these matrices are inverses of each other, right? So these kind of matrices which have their inverses, we will use those matrices for the multiplication purpose. And one thing you have to keep in your mind, that we need to deal with a pair of 4 bytes at a time. Okay, so we'll be multiplying those 4 bytes with this constant matrix, and in result we'll be getting a column matrix once again. So this is the operation at the encrypting end, which we call as mix columns. So this mix columns transformation operates at the column level, which I already told you that this is the state and you will consider a column out of it. Okay, and we'll be multiplying this column with the constant matrix, which we are doing over here, and as a result we'll be getting a mixed column. Okay, and the resultant state will be having this column which we are getting as a result over here. So it will transform each column of the state to a new column. So that is the thing which this mix columns operation does. Now, the operation at the decrypting end is called inverse mixed columns, and this transformation is basically same as a mixed column transformation, and these two operations, they are inverses of each other, right? So the thing which or the changes which we have done at the encrypting end will be reversed at the decrypting end. Fine. So this is an example of mixing state, wherein this is the mix column step, okay, which is performed at the encrypting end. So after using that constant matrix and considering this state column wise one by one, we get this state as a result. And after we apply this inverse mixed column operation, then we get this state back, which was the original one, right? So this is how this mixing is done. Now the next and the last operation of any round is key adding, right? So we are done with the sub byte, shift rows and mixing. So the last operation and the most important operation is adding of key, because this key makes this cipher secure, so that any attacker could not intercept the message. So adding the key into the message is a very essential part. So the operation which we have under this transformation step is called add round key. So if you remember, in the structure also we call this operation as add round key. So this add round key, it proceeds one column at a time. Again, we are making use of this state. We are using that state column wise, right? So this add round key adds a round keyword with each state column matrix, and the operation it is in add round key is matrix addition. So in mixing, that operation was multiplication, but in add round key the operation will be addition. Okay, we'll be having a matrix and will be adding that matrix to each and every column of the state, and as a result we'll be getting a new column, okay, which will be the resultant state. The add round key transformation is the inverse of itself, of course, because we are performing this addition operation, this matrix addition operation. So this will be inverse of itself, right? So this is the representation of add round key transformation. So here we are dealing with the one column at a time of the given state. So this state which we have got from the mixing transformation operation. So this is the output of mixing transformation, right? So we will be using this column of this particular state, and then we'll be adding the matrix column with this this will be the keyword, right? Which we take out of the key. So that thing will be discussing in later slides कि कैसे हम लोग ये keyword का use करते हैं. This is a word out of the given key, which is 128-bit key, right? So that process we'll discuss later, but right now you need to understand that what is this add round key transformation. So we'll be performing this matrix addition operation over here, and we'll be getting this changed state, and this will be the result of it, right? So in this operation, I told you, if you remember, that the number of keys which we use in AES is one more than the number of rounds, right? So we need to generate one more key, then one more key than the number of rounds we have. And that key is used, if you remember, we had the initial round which was called the pre-round. So one key we need for that round, and other keys we need one key for each and every round. So for that purpose, we need to expand the keys. Okay, so this is, the important or the crucial part of this add round key operation, which is called key expansion. So to create round keys for each round, AES uses a key expansion process. Okay, and if it is telling you the same thing, that if the number of rounds is nr, then the key expansion routine creates nr plus 1 128-bit round keys from this given single cipher key. So initially we have this 128-bit cipher key, and out of this cipher key we will be creating this much of keys, which is number of rounds plus 1. So this process of creating this much of keys is called key expansion. So we have key expansion in all these three structures of AES, which use 128 bit of key, 192 bit of key, and 256 bit of key. So we'll be discussing this 128 in detail, and after understanding it, it will not be hard to understand this key expansion process of 192 and 256 bit key, right? So this process, what does it do? It simply it will create the round key word by word. So what will we be doing? We'll be dividing the key into four words, right? And each word will be of 32 bits, right? Because in total we are having 128-bit key. So we can say that we are having four words in it, because each word is 32-bit long, right? So we have four words in one key. So we'll be creating these keys word by word, where word is an array of 4 bytes, right? So we'll be having 32 bits in each word. And this routine, this key expansion routine, it creates 4 into nr, which is the number of round, plus 1 words, which means it takes 128-bit or 192-bit or 256-bit key, depending on कि हम कौन सा AES यूज कर रहे हैं, कितनी कितनी बिट की की के साथ, and it will expand into array of 44, 52 and 60 32 bits word respectively. Now how do we get these much of words out of these keys? Now if you remember this 128-bit key, when we use 128-bit key, then the number of rounds we have in AES is 10. For 192-bit key, we have 12 rounds, and for 256-bit key, we have 14 rounds. So if we consider this 128-bit key with 10 rounds, then the number of words created according to this expression will be, this will be 10 plus 1, which is 11 into 4, 44. So 44 words will be, the key will be expanded into 44 words, right? So initially we'll be having 4 words, and out of those 4 words we'll be making 44 words, right? So that we can make that use of we can make the use of that initial cipher key, which is of 128-bit key, to create 11 different keys for each and every round, right? And because each key is 4 byte long, so we can say that sorry, each key is each word is 4 byte long, so we can say that we are generating in total 44 words, right? So in 192-bit key, we use 12 rounds. So 12 plus 1 is 13, and 13 into 4 is 52. So 52 32-bit words will be there for this 192-bit key. Fine. And just like this, we have the 60 words, each of 32-bit for 256-bit key. and we represent these words which we make out of keys like this, which are represented over here. So for pre-round, we'll be using the key as it is. Okay, these are the words which are made up of the cipher key as it is, which is W0, W1, 2 and 3. So these four words will be using for pre-round. Then we will be creating the rest of the words, which is from W4 to W43, because in we are talking about 128-bit key AES. So we'll be generating 44 words in total, right? So here from 0 to 3 we have taken as it is from the key. Then we have to generate from W4 to W43, right? So these 40 words we have to create by expanding the key. So this process is called key expansion process or key expansion routine. So we'll be discussing this process in detail, that how do we convert this initially given 128-bit key or these four words of key into 44 words of the key, so that we can make use of a different key which is made up of the initial cipher key for each and every round, right? So we will be now understanding this process, this key expansion process. So what we do is we start by copying the key into first four words. So that is the thing which I was telling you over here, that for the pre-round or for the initial step, we consider the key as it is. So we have broken this key into four words and we have considered these four words as it is for the first round. So this first round is called here pre-round. Okay, so the actually the first round starts from here. This initial round we call as pre-round, right? So we start by copying the key into first four words. Then we loop, creating words that depend on the values in the previous and four places back. Now what does this point mean? It says that this W4, so now we have to start creating this W4. So this W4 will depend on the previous words which have appeared over here before it, right? So this W4, W5, all of these will depend on the previous words. With this W1 may depend on W0, W1, 2, 3. So this process we will understand that W4 depends on which of the words, W5 depends on which of the words, and how this process goes on, right? So it says that it depends on the values in the previous and four places back. So it means that W4 will be depending on the word which is previous to it and which is four places back to it. Okay, so we can see that फोर प्लेसेस बैक इसमें कौन सा वर्ड है? We can see from here, this is 1, this is 2, this is 3 and this is 4. So W4 will be depending on W0 for sure and one more value which is previous to it. So in this case we do not consider this W3 previous to W4. Okay, we'll be considering a temporary word for to call the previous word of W4. For W5 we can say that W4 is the previous word, right? Because we are in the round 1. Okay, so this value we do not consider as the previous value. So W5 will depend on its previous value, which is W4, and the value which is 4 steps back to it. So 4 steps back W5 का कौन सा होगा? This is W4, this is 1, 2, 3 and 4. Right? So W5 की जो value है that will depend on W4 and W1. So So dependency का यहाँ पे क्या मतलब होगा, will be performing some operations on W4 and W1, and as a result will be getting the value of W5, right? So in short, we can say that each and every word will depend on the word which is above this in the table, right? So if we want to see for W6, then we can say that it depends on W2, because this is the entry which is 4 steps back to W6, right? So this W7 will depend on W6 and W3, and this process goes on. So that is the second point. This it tells you. So now we I've told you that this W5 is simply dependent on W4 and W1. Now how do we deal with this initial value, the initial word in every round, that is with the W4, W8 and so on. So for this we have this rule which says that if this word subscript is divisible by 4, then we say that this word this word depends on the word above it, okay, or we can say the word which is 4 steps back, and one more temporary word which we call which we represent as t, right? So I'll show you the diagram now. Now you will understand it. So initially what we have done is we have created word out of these 4 bytes of keys, right? So these 4 bytes, they make one word. So out of this whole key we have created 4 words. Fine. Now this is pre-round, right? Now this is round 1. This is round 2, and this is round NR, right? Or we can say round 10. Okay. Actually this is 11 because we have NR plus 1 rounds over here. Okay, so what we do is, here you can see that this W4 we are getting from W0 and T4, which is a temporary word. Fine. W5 we are getting from W1, the word which is above this, and the previous word, right? So we can say that the words which are which have their subscripts as subscript divisible by 4 or multiple of 4, they are calculated using the word which is 4 steps back and a temporary word. So how do we calculate this temporary word? We have this way of calculating the temporary word. Okay, so what we do is we perform some operations, and then we get this temporary word, and those operations are rotation, and then substitution, and then this constant value we have. I'll tell you the constant value for each and every round, right? So this value is different for each and every round. We have the table for this. So we simply rotate the word, then we perform the substitution operation, and then we XOR the output which we get over here with this R cone value. Okay, this is a constant value. We XOR both of these values, and then as a result we get this temporary word. Fine. So this W4, or the words which are multiple of 4, they are calculated using this way, and the words which are not multiple of 4, for that will be making use of the previous word and the word which is 4 steps back. right? So this process is, written over here. You can see that the first four words, which are W0 to W3, are made from the cipher key, which we have done over here in this step. Then the cipher key is thought of as an array of 16 bytes, which is from K0 to K15. The first 4 bytes become W0 and the next 4 byte become W1 and so on. Now, the rest of the words, which is, from W4 to W43, they are made up as follows. So, if I mod 4 is not equal to 1, which means the subscript of W is not a multiple of 4, then what we do is we consider the previous entry, which is, I minus 1, okay, because we are creating wi right now. So this is I minus 1 XORed with the word which is 4 steps back to it, right? So we will be creating new word using this expression. Now, if this I mod 4 equal to 0, that means if the subscript of word is multiple of 4, then what we do, we calculate this temporary word, which we represent as T, and we add or we XOR the value of this temporary word with the word which is 4 steps back, right? And this temporary word is calculated as, we apply two routines to it. What one is a subword, which is substitution, and this rote word, which is rotation on wi minus 1. So we have to take the previous word, okay? So if we are calculating the value for w4, then we have to perform the operation on w3, okay, this rotation and substitution, and then XORing with the R constant, right? So this is how we perform this key expansion operation. Now this round constant, uh, we have a table with us which tells us that for which round we have to use which round constant, right? So this is the table. So for round 1, this round constant will be having this R con is short form for round constant, right? So for round 1 we'll be having this constant, for round 2 this constant, and so on. So in this round constant, the the left 6 bits are zeros, and we have value for only 2 bits, right? So that value is fixed, this is predetermined, we have to use this table as it is. Right, so this is how this expansion process goes on until we reach to the last word, or until we generate the last key for the whole AES process, right? So this table is an example which tells you, or which shows that how the keys for each round are calculated, and we are dealing with this 128-bit cipher key, which is agreed upon by the sender and the receiver. And this is the key, this is the initial key, the 128-bit cipher key we call it, okay? And out of this cipher key will be generating the round keys, okay? So we'll be having this 11 rounds, um, if we add the pre-round as well, okay? We will be having 10 rounds, but if we add the pre-round as well, we can call that we are having 11 rounds. So this is the pre-round, wherein we are using the key as it is. You can see it from here, okay? This is the key which we are having with us, right? So after this, when we come to this W4, we have to calculate the value of key. So this is the value of T for each and every round, which is calculated using that R con table, and this rotation operation and the substitution operation. So one value of T is shown over here after calculating it. Okay, so we can use this value of temporary word for the round 1. So just like this we can create, or we can find out the value of temporary word for each and every round. Okay, so the main concern or the extra step is required for these words, okay, whose subscript is multiple of 4. Rest of the words you can calculate by the existing words which you already have with you, right? This W5 will be calculated by applying an XOR operation between W4 and W1, and this process goes on to find out all the round keys, right? So this concept of weak key, which we were having in DES, is not an issue in AES. So it it tells you that if you assume, because weak key was, if all the bits of the key are zeros or ones or half zeros and half ones, so that was the case of weak key. So if we assume that all the bits in the cipher key are zeros, then if we generate the round keys out of this cipher key which is all zeros, then in the pre-round and the first round they will be same. Okay, they will be having all zeros in this, but in the second round the first word will match the third and the second word will match the fourth. So this pattern will be there in the second round. Okay, in pre-round and the first round the value of the key will remain same, but in the second round the key will be in some pattern. Okay, and after the second round this pattern disappears and then the every word is different. So this problem of weak key which was there in DES is not an issue in AES, right? Now this is the key expansion in AES 192, wherein we have 12 steps, okay, and the length of key is 192. Now since the length of key is 192, so we'll be creating 6 words out of it. Okay, so instead of creating 4 words, we'll be having 6 words out of the key, right? Because of the increase in the size of key. So what we do is, in this we have to check whether this word is the subscript of this word is multiple of 6 or not. In that case, in 128-bit key we were checking whether it is a multiple of 4 or not. In this we'll be checking whether it is a multiple of 6 or not. So if it is a multiple of 6, then we'll be dealing it, as we dealt with the W4, W8 in case of AES 128. So यहाँ पे भी हम लोग एक temporary word का use करेंगे and will be XORing it with the word which is 6 steps back now. Okay, because we have 6 words over here. So this process will go on, okay, up to the last round. Fine. So this is about AES 192. In AES 256, we have the key size as 256. Okay, and the total number of words we have is 8. So the pre-round key will be using the same words as the cipher key, and then this this word which is the ninth word whose subscript is 8, this will be considering you know as we have considered the W4 in AES 128 and W6 in AES 192. Okay, so we'll be adding this temporary word and the word which is now 8 step back. Okay, so ultimately the word which is above this will be taken into consideration for that particular word. So यहाँ पे W9 के लिए will be considering this W1 and the previous word. So the process will remain same. Here, along with this 8, we have to check that whether the subscript is multiple of 4 or not. So if the subscript of word is not a multiple of 8, then the process will be same for these all of these words, right, which is involving the previous word and the word above it. And if the subscript is multiple of 4 but not multiple of 8, then we perform a different operation on the previous word, which is the substitution. Okay, so on the bits will be we will be performing this substitution operation, and as a result we'll be getting this UI word. Okay, so you can see that this UI is being applied or being XORed with the words which are multiple of 4 but are not multiple of 8. Okay, so this thing we have to keep in our mind. Rest of the things are same. Okay, so that is the key expansion process in AES. Right, so now we have completed the structure of the round in AES, wherein we discussed about the transformations which the state goes through after passing through each transformation operation.